Jens.
You're too kind, Ingo. That's great. So thanks so much indeed. Thanks for the kind invitation to this wonderful workshop on actually the very topic that actually motivated me to work on quantum information in the first place, I should say. And thanks for the invitation to Benasque, kind of. I'm embarrassed to be able to participate only electronically this time, as Benasque is really one of the places I like most. And I have been there earlier this year, but it is what it is. So, entanglement in action. So this is basically what this talk will be about when we have a look at what could be called the smallest computable entanglement monotone, and to spice this up with a bit of action, the practical detection of entanglement and notions of benchmarking. Now, entanglement was quantum information's first love, and it will be its last. So from a conceptual perspective, one can argue that entanglement is really the very element of quantum mechanics that makes it quantum. So by virtue of Bell's theorem, one can say that entanglement is the feature of quantum mechanics that renders it different from a classical statistical theory. But more to the point of entanglement being in action, it's probably fair to say that in all hands-on like practical applications of quantum information, it does play a key role. The almost religious credo that entanglement is a resource in quantum information has probably been stated a bit too often and repetitively in paper introductions, but then, well, one can make a pretty strong point that in basically every application it is needed. So for this reason, over the years, methods of quantifying and techniques of experimentally, feasibly measuring it have remained important, and on both topics this talk will add a bit of a new twist, if you want. So to be a bit more specific, so entanglement is indeed required, say for quantum computational speed-ups. The lesson to be learned here is that yes, the fine print does matter, and the precise role of entanglement or what it plays in quantum computing is not always completely obvious, but what is a fact, say that if you say if the quantum computation is such that the Schmidt rank over any cut is bounded by a constant over the entire computation, then an efficient classical simulation follows, as one can basically tensor contract the respective tensor network in classical efficient terms. So these considerations are actually quite timely. We're just finalizing a monstrous RevModPhys review article on quantum random sampling schemes for allowing a quantum computational advantage. And we are going through all the fine print, and while these experimental efforts are exciting, so are advanced classical simulation methods based on tensor networks. And on a high level, one is like pinching holes and then crafting clever contraction techniques that exploit in one way or the other that not so much entanglement is being generated along the way to get good approximations, and this gives rise to a pretty cute and exciting race between the quantum implementation on the one hand and the classical simulation on the other hand, that's basically making use of tensor contractions of such a kind. So to add to the how important it is to look at the fine print here, so one can also, I should say, have too much of a good thing. Say you entangle along the way in the quantum computation, you have to, but at the very end you better make sure that you're not too entangled before you do the measurement. You should, before the measurement, have little entanglement at the end of the day. And if you think of like measurement-based schemes for quantum computing, it's kind of interesting that if the geometric entanglement is larger than n minus polylog n, where n is being maximum, then the whole thing can be not only efficiently simulated, but running the same classical control around it. So you can be too entangled to be useful, which is also a bit ironic when you think of it. Or say, take quantum key distribution. One also needs it. So entanglement-based schemes require entanglement. Well, as the name says, to get a positive key rate. What is maybe less obvious is that this also remains true in in prepare and measure schemes such as BB84 when the setting is like properly interpreted as a kind of respective entanglement-based scheme that would reflect the prepare and measure scheme. So far so good. So this talk contributes to technical results, which hopefully do not sound too patronizing. The first one is going back to the ancient days of quantum information when we ask, great, entanglement is important, but how can entanglement be most reasonably quantified? And specifically, we will ask what the smallest computable entanglement monotone could possibly be. That's not a timely topic, I can say that. I still love to do it. That's maybe the nice thing about working in academia, that while you can spend most of your time working on timely topics that are related to aspects of what the quantum industry is doing, you can also work on things that come to your mind. So we will here have a look at how to quantify entanglement with a new reasonable quantity. And like to turn to the action part, we will also think of how entanglement can be experimentally feasibly measured. We will see how known or random evolutions come into play in one way or the other to make this possible. And we see that random sequences play an important role here. And we also ask how we can go beyond plain vanilla randomized benchmarking, think of more sophisticated ways of data processing and not so much of running new experiments, but basically, now I'll give it away, presenting a prelude of what Ingo has to say tomorrow, because I think his talk will really precisely start where my talk ends today. So see this as a bit of an invitation to Ingo's talk tomorrow. Wonderful. So smallest computable entanglement monotone. Now, what is this? It's not a new question, by no means. I mean, this when I started my PhD, this like the question of how to reasonably quantify entanglement was the talk of the town, and it's still an interesting question. In many ways, some questions also have been left open, and not like maybe abandoned and not solved necessarily. And this is a question of this type, if you want. So the highest level, one can think of quantifying entanglement on the axiomatic and the operational level, where the axiomatic level would basically argue that there should be certain requirements that have to be fulfilled so that we would reasonably associate a given quantity with an entanglement quantifier, whereas the operational approach would say there's a certain task I want to do and what are the best possible rates I can achieve in accomplishing this given task. And here we will basically have a look at both questions at the same time. So the paradigm of entanglement is that of a separated lab paradigm. There's a lab here, there's a lab there, and entanglement is a property of a composite system, a part here, say A, part here, there, and you can do stuff here, and you can do stuff there, but it's kind of inconceivable that when like one lab is in Berlin, I hate to break it, or the other one is in Benasque, then clearly you can do local things in your respective labs, but there will be no joint action along the way. So we would think of classical quantum operations that take measurements in the respective labs, and we can call each other and can coordinate the action by means of classical communication about these respective measurement outcomes. Now, commonly, one has to live with the fallacies of life. One has something, a given state, noisy, dodgy, warm and wet, rho, but one would like to have a different one, maybe a cleaner, purer, a more entangled state, a final one, and one asks in what way, what sense and at what rate one can convert a given state rho into a desired final state sigma. And this is not necessarily meant on the single short level, although this makes perfect sense also, but commonly also in particular in the sense of an asymptotic rate, that you basically ask what rate you can achieve of starting with n copies of the initial state rho, where you want to go to m copies of sigma approximately, and ask what the best possible rate m by n you can achieve to get asymptotically perfect copies in the large n limit. That's like, it's not an accident that this looks like classical information theory. All this theory is like deeply rooted in good old Shannon-style classical information theory. So the mother of all entanglement measures is the so-called distillable entanglement that basically captures the resource character of entanglement. You ask, what is the effective content of maximally entangled states you have in a given quantum state, pure or mixed? And specifically, it's the largest rate of approximately perfect maximally entangled pairs that can be created from many copies, many specimens of a given state world. So that's a way of putting it here. So there's a kind of a dimension D that can be large. It takes a moment of thought that this is really the optimal rate of getting a number of maximally entangled copies out with protocols that do something here, do something there. They call it like an LOCC protocol that doesn't have to be perfect, but where the fidelity with respect to the maximally entangled state would become, it should go to 1 in the asymptotic limits. It would become asymptotically perfect. I had a trace norm there before, apologies, for many copies. That's the best rate, that's the effective number of maximally entangled states that are given in a specific resource state. So that's great. It's very meaningful, very operational, very hands-on. It's really the thing that makes things go round. But that said, the distillable entanglement is a beast. It's very difficult to compute. The only formula I'm aware of that's for like a rank 2 Bell diagonal state. It's a ridiculous formula. Interestingly, and maybe ask me about it, I've thought quite a bit about this in the past. It may even be uncomputable as a quantity, which is an interesting state of affairs. Anyway, it's a meaningful quantity, but we can't handle it. So over the years, people have been thinking about bounds, specifically upper bounds that would conservatively bound the entanglement content in a given state at hand. And there's a couple of suspects around. A commonly used quantity is the so-called logarithmic negativity. That's basically the one norm, the trace norm of the partially time-reversed state, or the partially time-reversed object of a given input state that has a number of reasonable quantities, and also actually, in fact, is an upper bound to distillable entanglement. The tightest known bound to the distillable entanglement is the so-called Rain's relative entropy. It also came up a long time ago. Again, this is not like, look at the numbers of years that are being cited here. It's a kind of acute quantity that kind of combines the relative entropy of entanglement and the negativity, but in a kind of funny way, what's optimized over is like sigma. That's on the right-hand side of the ReLent, and also in the negativity. It is what it is. That's the Rain's relative entropy as an upper bound through the distillable entanglement that was kind of shown using ideas of semi-definite programming at the time. Now, this is great. It's indeed a bound. It's the tightest known bound for the distillable entanglement. It's computable as a convex program. That may not be entirely obvious, but if interested, I can say a bit more about this. Indeed, it's a convex problem. But annoyingly, it's like not known to be an entanglement measure. So a selective monotone in its own right, because the one of the minimum things you really want from a quantity to be a reasonable entanglement measure is that by local operations you can't increase it. It would be kind of funny that if you have a state shared between here and Mars and you do something here locally, and then you can kind of increase the entanglement with Mars, at least not on average. That would be kind of strange. So this is like one of the ways, the kind of the defining feature of an entanglement monotone is that it would be like not increasing on average if you perform a local operation together with classical communication. This can have many rounds. I think Andreas has a beautiful paper that shows that a k-round protocol is strictly less powerful than a k+1 round protocol for all k. But never mind, so you collect them all in kind of super indices and you have like lots of outcomes, and you say, no matter what you do, on average, you wouldn't want this dude to become larger than the initial value. So that no matter what you want, you want the quantity to be a selective entanglement monotone in this sense. So can this be proven to be a meaningful entanglement monotone? And this question was sitting around. In fact, what happened, this is kind of sorry, I found this funny. So it happened that Mark Wilde asked me or not me, anyone, that's how Twitter works, on Twitter, like whether has anyone proved that the range relative entropy is a selective LOCC monotone. And he was citing equations from a preprint together with a book, actually, that he wrote together with Sumit, his former student, now a postdoc of ours, a wonderful guy who wrote this comprehensive 1,000 pages book, where the question was left open whether this nice, tightest possible upper bound to the tightest known upper bound to the distillable entanglement is actually an entanglement monotone in this sense. And I looked at it, I said, oh, wait, maybe that is right. I had an idea, and I said this pretty much immediately. He said, yeah, thanks for your reply. I'm aware of this, written in the equation I referenced. Okay, fair enough. But it's not clear to me that this observation is sufficient. This will get LOCC monotonicity, but not not a selective monotonicity. That was in September 18. I said, yeah, then I said something. I said, oh, that still works. I will try to present a write-up over the next days. Well, that put me under pressure. That's November, so not quite the next days. But anyway, so hi Mark, I sent you an email that contains a draft, and I think I know how to show this. It's a cute little insight. And this kind of was a starting point, and then it kind of developed, and we ping-ponged stuff, and that kind of developed into a paper, which is kind of an interesting way of collaborating. I found this actually quite funny. Anyway, the upshot and the high-level argument of this proof is like ideas from the early zeros. So the quantum relative entropy in its plain vanilla version, but also in the PETs, so the geometric Rényi relative entropy version, has a kind of a classical, as a kind of direct sum property for classical quantum compounds, where you keep a kind of classical flag of outcomes. That's kind of helpful. Then you use for all of these relative entropy data processing, and you can use a property that's actually quite similar to a property that enters the monotonicity of the logarithmic negativity, so the kind of a trace norm property of partial transposes that you put in. There's a scaling property of the quantum relative entropies, so that you can, if you scale the right-hand side, you can kind of shift terms so that you can massage terms, and the steps are basically massaging the probabilities right, so that you can put things together to distribute terms to make it possible to use the concavity of the logarithm, so that you really get the desired right-hand side. It's actually for a slightly larger class of operations, the PPT operations, but never mind, they include the desired local operations with classical communication. So putting it all together, it works, and yes, it is what you want it to be, and it is a selective entanglement monotone that reasonably quantifies entanglement. That's reassuring. You can see this quantity is the most conservative upper bound for the distillable entanglement, but it also has the quantities, the properties that you would want from such a measure, which you can show. So that's really maybe the way to do it. So this is a first result. The paper goes on with lots of technical results that follow up from this. We have results on the generalized PETs, the geometric, the sandwich Rényi relative entropies. We looked a bit at probabilistic approximate distillable entanglement in the asymptotic limit, where you also allow for finite errors that don't go to zero for the large n limit. We converse upper bound for this probabilistic approximate distillable entanglement, and also one can see the whole thing as basically originating from a acute resource theory of basically unnormalized quantum states, which is a kind of fresh picture, because you can derive this being the upper bound to the distillable entanglement in like 3 lines or so. That's actually an interesting picture. Ask me about it if you're interested. So the lesson is, yeah, the range relative entropy is a very reasonable quantity. It's the smallest known computable entanglement. It's like there's the distillable entanglement, the entanglement cost are the smallest and the largest reasonable measures of entanglement, as the 3 of the 4 Radetzkys have shown in 2000. That's really just a bit above, and that's the advice is if you have to plot a quantity and so on, use this. That's the most conservative one, but it also has the desired properties that you would expect from such a thing. So this was really fun to work with Mark. I must say that was really a highly pleasant and fun endeavor to ping pong things back and forth. That was actually quite fun. Which brings me to the next part on feasibly measuring entanglement in a more like hands-on, in a more lab type sense, bringing also in ideas of benchmarking in a way. So changing gears, how can entanglement be feasibly detected? Meaning experimentally feasibly detected. Well, what's the issue? You go there, you measure, and you have entanglement or not. Well, the trouble is that this is not usually how it works. Commonly, the right measurements are not quite available. You could just do one type of measurement in the lab. You would not be able to like do X and P measurements at the same time, but say particle number measurements or so. That's a strong limitation that just one type of measurement is available. So there's kind of 3 levels of advice that I give away, and that's also paving the road ahead that Ingo will sketch out tomorrow. So 3 things. First of all, one can trade known dynamics against simple measurements. It's a brutally simple idea, but it can be very helpful if you just have a certain basic type of measurement that you can use known dynamics beforehand to make these measurements work. Then randomness is not a bad thing, but a good thing. Use it. It's a very powerful tool, as I will say, but Ingo will say even more about tomorrow. I will kind of advertise this a bit and we'll start talking about random sequences in a way. And finally, strive for robustness. If you can, your preparations, your state preparations, your measurements, everything will be a bit faulty. You better have something to say even when everything is a bit faulty and you still want to get reasonable diagnostics about your quantum technological device. So on the first point, I will motivate this with an example from non-equilibrium physics, so for something completely different, but you will see in a second where this is going. Coming from the old question, like Pauli type old question, how closed quantum systems actually equilibrate and thermalize, and how quantum mechanics and statistical mechanics with all its maximum entropy ensembles can be actually reconciled. There's a lot to say about this, not for today, but the upshot is that closed systems can, of course, never truly equilibrate and thermalize, but what can be true, and that's what's generically happening, is that local expectation values can, for most times, take values as if the entire system had equilibrated and thermalized to a maximum entropy state. So many flavors and readings, this has kept me busy over the years. A setting where this can be very nicely probed in the lab is that of cold atoms on atom chips, which are like chips with suitably controlled potential, so that you can have like basically 2 tunnel coupled wires on top of the chip that you prepare in 2 Bose-Einstein condensates that can tunnel along the way, and you can think of the difference and the sum quadratures, and this together can be seen basically as a 1 + 1 dimensional quantum field with density and phase quadratures. Now, this is great, and then you can have lots of control, and you can ask questions, what's going on, and I was super happy to see when our friends in Vienna sat down and were looking at something that kept me so busy for many years, on looking how systems would turn into maximum entropy states in time, or at least apparently turn into maximum entropy states, and for that type of system would be like a Gaussification in time, where you can see at the right combinations of moments, of cumulants if you want, and see really how the system apparently not only equilibrates but goes to a Gaussian type maximum entropy state in time. So when I saw this, I was super excited and was thinking like, oh, that's great to see this under nicely controlled conditions in the lab. But there were open questions like, what's going on? The initial state was really hard to tackle. It was difficult to see what's going on, what transport one has, whether entanglement was there in the system. And the trouble is, first the good news is that quantum field systems do equilibrate and they gaussify to maximum entropy ensembles. That's great. So this prediction of StatMech, if you want, can be measured and monitored in time. That's nice. But the trouble is that the way it's set up, you can only measure phases, or rather phase differences, and never densities. That's has to do with how this is set up. You can measure densities, but of the wrong quadrature, of the sum quadrature. That's completely noisy and there's absolutely nothing in it. You can't really measure the density of the right conjugate quantity that is the conjugate quantity of the phase difference. And that's super annoying. And you ask, is the state entangled? Well, you don't know. You can only measure one quadrature. What's the initial condition? Is it Sine-Gordon-like? Is it strongly correlated? You don't know. You can only measure one quantity. Is it, no matter what you ask, you are stuck because you can only kind of measure one variable, but not the other one. So how can you measure the missing quadrature? And, you can't. It's missing. That's in the ontology of a missing quadrature. But what you can do is you can invoke this basic principle that I said earlier, or mentioned earlier. And that's like brutally simple, but it's really nice to see that this works so well in practice, even when the dirt and the misery and pain of experimental implementations comes on top. This is really something that works extremely well. And the upshot is you have like a 1 + 1 dimensional quantum field. So in these field operators, you would see the Gross-Pietewski profile sitting here. But well, you can think of a Fourier transform of the continuous field into a discrete mode momentum space. But in the non-interacting regime, when you can tune this to, this momentum space evolution would be just clocks going around at their respective speed, like a number of modes, maybe many, but in frequency, like lots of clocks that go around, and that's the full-time evolution you have in the system. And that's something you can classically keep track of if you know the speeds of the clocks at the given time, and the momentum at one point is the position at the other time, and so on. You kind of go around in this fashion. And what you can do is, and then you can go into the lab, or ask your friends to go into the lab for that matter, and you take many data points at different time slices, and then you retrodict in time classically efficiently, and evolve under the effective model to then basically make it a recovery process of finding the most likely density profile in 2-norm under the positive semi-definite Heisenberg constraint that constrains the covariance matrix to be a physical covariance matrix. For those who are familiar with the theory of compressed sensing, there's a bit of a theory background that you really need this type of Heisenberg, this semi-definite constraint to make it work. Though what it basically is like a symplectic compressed sensing recovery of the respective frequencies. And that's it. And that works extremely well in that you can really take data where a system is like going down, it's relaxing, and then you take data at a point where the system's already dead. But you can look into the other quadrature you can't directly measure, and you can say, oh, this is so coherent, there later will be a point where there's a recurrence where the system goes up again. And it's kind of dead, and then you say, there's the recurrence, and you measure it, and bam, there's the recurrence just at the point where you think it should be. It's very nice, it works well, and in the meantime, there's like a routine thing in their lab where you can, whenever there's a data point, you would run this on their data to basically look at different quadratures. So, lesson, genuine quantum readout is possible. You can look at entanglement, coherence, transport, and so on. Entanglement is difficult, we're just looking at it, but you can look at coherent quantities in the lab under nicely controlled conditions with this simple, accessible measurement. Similar ideas also work for cold atomic systems, say, like in optical lattices, where you can only reasonably, except from Fourier type measurements, measure particle numbers in so-called quantum gas microscopes. This is an interesting setting. There was even an entire conference dedicated to this not long ago, where again you can say, can I trade in simple measurements or relatively simple measurements with known dynamics on the level of some tuned interaction. If you can tune the system to a non-interacting Hamiltonian, say of fermions or bosons, then you can, with number measurements, only get a lot of diagnostic information about the quantum system. And in this work that came out not so long ago, we also go into the nitty-gritty bits of experimental desiderata, looking at how plausible the Feshbach resonances are. So that's a pretty close to experimental paper if you want. But the upshot is, you can again do a semi-definite like convex recovery of recovering fermionic covariance matrices, doing the right either fixed or random sequences in moment space, and that works well, at least in theory, where you can get recovery of the respective covariance matrices or the second moments, and you can look at transport, entanglement properties, and so on. So we've looked into this. So one can again get tight bounds to, say, distillable entanglement. There's an interesting insight that maybe this inequality is worth noting. So there's an inextremality of Gaussian states over entropies, but here it's actually over differences of entropies, which is interesting. So that the hashing bound is actually extremal for Gaussian states, which is kind of interesting because it's a difference between between entropies. But it's still good to know because you can just measure your stuff and you can get a bound on, say, the distillable entanglement without having to assume that the system is Gaussian in the first place, which you wouldn't know anyway, because that would be an unreasonable assumption. That's not something you can measure, but you can still get nice bounds at the end of the day. So the lesson is that with coherent quantum dynamics and simple measurements, don't tell an experimentalist, never call it simple, but you know what I mean, like particle measurements from, say, quantum gas microscope, they allow for coherent quantum readout and entanglement estimation, where you trade in the known dynamics, where you can do retrodiction with the measurement that's given in the setting. Randomness measurements, and that's a theme that I start here. Ingo will catch up with this and will build on this. But I'm sure there's also lots of other talks in this during this week on random measurements. It's a pretty hot topic these days on thinking of shadow estimation and the usefulness of random measurements in one way or the other. I will not mention random measurements in tensor network state that I've advertised in the abstract, but ask me about it if you want, because that's a kind of cute application of a frame or a one design. So can you use like random sequences before the measurement to get going? And this is an idea that we looked at many years ago, again, like in 2013, where we looked at combining ideas of efficient state tomography, like matrix product state tomography, which you can do if you can get the reduced density operators out, then you can recover the respective matrix product state, which is a reasonable hypothesis for a family of quantum states that would be like ground states of gapped phases of matter. And you can indeed recover states from that family of states by like recovering reduced quantum states, like the concept class if you want in learning terms. And that in turn can be obtained by certain random sequences that would constitute approximate unitary designs. So like collections of unitaries that would approximate the moments of the H measure up to moments t that would give rise to a approximate unitary t design. So let me end the talk with, because I promised Ingo not to go over time, and I like to keep promises. So let me end the talk by like advertising what Ingo will say tomorrow at ideas of uplifting like randomness to the setting of random sequences, where you say take a certain gate set and you would like implement random circuits from the gate set, and would do this many times, and you kind of try to get diagnostic information about the system from the random sequence at hand, so to see how randomness can help in this setting. In fact, there's a standard tool, it's a plain vanilla tool to characterize quantum gate sets. It's called randomized benchmark, where you basically say, if you think of the Clifford group, you would do random Clifford operations, and like you do this many times, like m times in a row, and this being a group, you can undo things in the last step, and then from the deviation from the identity, you can basically make a fit and see, you get interesting diagnostic information out, like insights about the average gate fidelity of the respective gates or gate set. And that's great because it's robust, or specifically gate state preparation and measurement robust. So the preparation can be a bit wrong, everything can be a bit wrong, but the way it's set up, you can still get meaningful diagnostic information out, which is important because in a practical experiment, nothing will be quite perfect. You want to have a handle on doing something when everything is not quite right. So this is the plain vanilla randomized benchmarking scheme. The first protocol that was set up even presented data, and all the building blocks of a benchmarking protocol were there, but there was no theoretical justification of this presented whatsoever. The first theoretical work was done by these wonderful gentlemen here, on which was basically already introducing the core idea of randomized benchmarking. Some of them are actually in the audience, I think. Based on Haar averages. That's wonderful, but it's not so practical yet because Haar averages can't be implemented in the lab efficiently. So there was something to be connected, but that was soon happening. That the order is a bit funny, but people looked at combining these two things with standard Clifford randomized benchmarking. But I've put it up. There's also monomial randomized benchmarking. There's linear cross-entropy benchmarking. There's C0 dihedral randomized benchmarking, real randomized benchmarking, the Clifford averages, that's the unification of what we just saw a moment ago, dihedral randomized benchmarking, complete randomized benchmarking, you name it. So there's lots of different schemes. When you go to these meetings, there's lots of shouting and discussion on what the right way of doing it is and what the data actually says and how it should be interpreted and what this has to do with the average gate fidelity and whether it's really true that you get exponential decay from these sequences, and it's a bit of a mess. So to my knowledge, there's kind of about like over 30 variations of randomized benchmarking. There's a bit of a confusion and disagreement on the interpretation, and what we wanted is to understand this, to have a framework that's general enough to encapsulate them all, have a sound mathematical basis, both for the quantum and the classical part, but also have a basis for new schemes at the end of the day. And this is what we did. It was a long and winding effort. Ingo, that will speak tomorrow, will pick up this line of thought. And this was a quite serious effort. So what is a randomized benchmarking scheme? What is all randomized benchmarking schemes? There's a group involved in one way or the other, some finite group. You have a notion of idealness, that's the reference representation. You do certain measurements, there's some initial state, there's a length and some end gate, there could be the identity or something else. Ask me about it, actually that's an interesting point. So that's kind of basically all possible ways you can think of a randomized benchmarking scheme. And that's the physics, the dirty, dodgy physics that's provided by the device. That's the implementation map. That's basically just the way the gates are actually implemented in the physical system. And the data you get at the end of the day are just estimated or estimators of the probabilities that you get out of the probabilities you get in the respective scheme. These are the kind of the data in one way or the other. And the fork claim, that's the fork law claim is, well, that's what people use, is that, well, if you're really too noisy, then you're dead. But if, as long as the implementation map is kind of close to the reference implementation, then one would expect the data to, in one way or the other, be like some linear combination of the decay of exponentials from which you can get the right diagnostic information. And what we did is we kind of looked at this and kind of tried to prove this in all generality. We did this and submitted this to PX Quantum. We were like super proud to be desk rejected within 10 minutes with a comment, we are not publishing review articles. We said, no, it's not a review article. It's a mother theorem of all randomized benchmarking themes. And then we politely explained this and so on. And then it was like revisited and so on. Now it's getting out any time. Like this week it will come out in PX Quantum. Never mind. To cut a long story short, so it's an involved proof, but on the highest level, it makes use of convolutions, of Fourier transforms, of implementation maps, and sees that the whole full randomized benchmarking scheme can be written, or the the whole scheme sandwiched with the initial state or vectorized initial state and the measurement can be seen as basically a multiple convolution in a way, so that one can define a Fourier transform from groups, but not into numbers, but into super operators where the mode levels are basically the irreducible representations of the respective group, and then you can use this kind of Fourier transform and can kind of transform this multiple convolution, basically using the convolution property into a product, so that you could ultimately get the sums of exponential terms at hand. And indeed, it's true that if you are close enough to the reference representation, say in the diamond norm, there's also other characterizations thereof, then indeed it is true. So the folklore claim is true that you indeed end up with this exponential decay of numbers, but you really get the quantity, and you even have a kind of bound on the right-hand side that really shows you how well this will necessarily work. That's about the theorem 1. That setting encapsulates all known schemes for randomized benchmarking that we were aware of or are aware of. But there's also a second mother theorem that's kind of on the classical post-processing that kind of tells you how to make use of the data. Ingo might say more about this tomorrow or not, but anyway, there's also a way of kind of rigorously looking at the classical data you get out and how you make use of this to get the right diagnostic information. This can also be used to interpret the classical data with recovery guarantees or with nice error bounds, which are rigorous and also practically meaningful. But this can also be used to devise new schemes for like analog randomized benchmarking that is coming out hopefully at some point soon. But there's also other schemes you can think of that are based on this generalized framework. This reference is not quite right, but this is a draft that will also come out on the archive at least, hopefully anytime soon. Last slide, Ingo will continue tomorrow on this, is that we've been working hard to uplift this, and kind of we close the cycle of using random sequences. And the advertising point I'm making here is that these random sequences are quite powerful, where you take a gate set, say random Cliffords, and then from that gate set you would perform random sequences and you measure. And that's all you do. It's the same thing. You do random sequences and you measure, and this stuff you give to the theorist, or to us for that matter, and you stare at it and you kind of see what you get out from these data. And indeed, you can think of like measuring sequence shadows in a certain way, and you can get the right diagnostic information out, so that based on that data, you can think of, say, gate set shadow estimation. So you can get you can do shadow estimation on the channel level. You can do full robust channel tomography, where you get full tomographic recovery or learning of the noise channel of the setting at hand. You can learn Pauli channels, or you can do things like crosstalk tomography, where when the gates are not quite right, you can see like how much crosstalk there is and estimate the crosstalk between gates. And the nice thing is, it's based on the same data. So we talked to like Thomas Mons in like around the corner in Innsbruck, and we said, Thomas, can you take data of a random Clifford sequence? He said, who are you joking? I mean, that's data we already have, plain vanilla. This is at least for small numbers of qubits, is stuff that we readily have available. It's kind of nice because it's like, well, we're joking, it's like one data to rule them all. So it's like one set of data where you do random sequences, and from that, depending on how you do the massaging and the post-processing, you get different quantifiers out, from like full tomographic knowledge about the full quantum channel, or like channel entanglement quantities if you want, to like basic average gate fidelities or crosstalk diagnostics. So it's like from one data you can get lots of interesting diagnostic information out, which is a nice way of doing it. And it's robust or spam robust in all instances. 44 minutes into the talk, I have an hour, but I would like to leave time for questions. So I think it's a good moment to not overdo it and come to the end and look out a bit, but also not that too much. So this talk was basically a journey on the old and the new, on looking at entanglement. So this talk has been concerned with entanglement, the key feature that makes quantum mechanics different from classical mechanics, if you think about this. And we started or we left the story with part 2 when we thought when you want to measure it, you want to detect this based on plausible data, you can do it. But there's kind of 3 take-home messages that sound terribly patronizing. I apologize, but if you do that, things to have in mind are, if you are restricted in your measurements, which you commonly are, think of trading this with known evolutions. It's a basic idea. It's like very obvious, but well, the devil is in the detail. You can often trade evolutions, for example, in the moment space of a discrete continuous quantum Fourier pair of a quantum field theory. You can trade in this known evolution, make simple measurements, and get a lot of diagnostic information out. In particular, you can detect entanglement. You can even quantify. You can measure entanglement with this in this fashion. You can exploit randomness. You should actually do it. It's a good thing. All these ideas of random tomography, random like estimating entanglement from random measurements, shadow estimation, beyond shadow estimation, this kind of channel stuff that I mentioned that is combining randomized benchmarking with shadow estimation. It's a good thing. Randomness is not bad, even though you should think I should fine-tune things. Don't do it. Make a random sequence and you will get away with it if it's smartly done, and there will be lots of other talks along this way exploiting randomness in one way or the other. If you can, strive for robustness. You will need it. Your preparations, your measurements, everything will be a bit wrong. Ingo might talk about the Hamiltonian learning tomorrow. I'm not quite sure, but again, robustness of preparations, measurement, and everything in the middle will be key. You will need it to make it work. And the first part, yes, I couldn't help it. This was, for me, it was just fun. It was a bit of time travel going back to my old life. So here the advice is basically when quantifying it, use the range relative entropy. It's a meaningful quantity. It's a selective entanglement monotone. It's also the smallest, the most conservative computable entanglement monotone that is known for that reason. So if you want to do something, want to get a plot for an entanglement measure out, use this range relative entropy. It's a reasonable quantity. That's maybe my advice. It's the thing to do. It's a good measure of entanglement that captures these things. Also, I should say it was really fun to work with Mark. He's a great guy, and to ping pong these things was really nice. There was no student involved, so we just did it together. So we thought it would be good to have a proper proofreader also for the paper, because some parts were a little bit technical, and it's good to have a further pair of eyes on it. So we thought we would look for the smallest possible proofreader that looked over our smallest computable entanglement monotone, and let this guy check it. So here you see the smallest possible proofreader doing this, but he didn't find a mistake, and we were quite happy. So I think I leave it at this. I leave time for questions, and I thank you very much for your attention, and I'm looking forward to the questions you might potentially have. Thanks for your attention.
Okay, thank you very much, Jens, for this talk. I think we can clap.